Thank you for the invitation to present. In this presentation, I'm going to address the question of how oblique rifting influences the continental rift evolution and oceanic spreading initiation. To set a broader context to this question, I'd like to start from the Wilson cycle concept. So the evolution of the Earth's lithosphere is primarily governed by the alternating phases of extension and compression, which determine the successive continental rifting, oceanic spreading, drifting of continents, then subduction, collision, and mountain building stages of the Wilson cycle. A crucial implication of this cyclic nature of plate tectonics is that the lithosphere carries all kinds of rheological imprints within the lithosphere, like compositional contrast, thermal anomalies, or pre-existing structures that were inherited from the previous Wilson cycle stages. This inheritance is quite important because all these pre-existing lithospheric features may influence the evolution of any subsequent tectonic processes. For instance, at the onset of the Wilson cycle, continental rifting tends to initiate over former orogenic areas because the inherited lithosphere there is often hot and weak and highly heterogeneous due to the presence of various crustal or lithospheric scale heterogeneities and structures. These heterogeneities may function as weak zones and influence the evolution and architecture of rifts by localizing the deformation. What is important to note is that these weak zones rarely align properly orthogonally to the direction of extension, thereby creating various oblique rift settings, like for instance in the different segments of the upper triple junction. In fact, it has been pointed out that most natural rift systems exhibit at least some degree of obliquity, so this vast number of oblique rifts and rifted margins worldwide inspired us to try to quantify the effects of oblique rifting on certain aspects of the rift dynamics, like the syn-rift magmatism or the oceanic spreading initiation. So to do that, we conducted a series of three-dimensional geodynamical numerical models to compare the continental rift evolution in orthogonal versus oblique rift settings. The two-way coupling we used between our thermomechanical and surface processes numerical models allowed us to do an integrated analysis on the strain distribution in the lithosphere, crustal faulting, partial melting, thermal evolution, and also surface processes such as erosion and sedimentation. Our modeling approach was to simulate oblique rifting as part of the Wilson cycle. So our initial model setup was an approximation to thick orogenic type crust with a weak mantle lithosphere above the asthenosphere, with a weak zone defined in the mantle lithosphere. That actually represents a hydrated suture zone inherited from a previous subduction and collision stage of the Wilson cycle. The orientation of this weak zone defines the obliquity of the modeled rift. That is this alpha angle between the strike of the weak zone and the extension perpendicular direction. So the higher this alpha angle is, the more oblique the rift is. The rifting is itself is modeled by applying a 2 centimeter per year divergent velocity equally divided between the two sides of the model domain. We ran a bunch of parameter tests, but today I'm only going to discuss the reference model, which was an orthogonal rift model, and a few oblique rift models with 10 to 50 degree obliquity. So let's see the results. This video should show the reference model evolution for orthogonal rifting On the top, we can see that the lighter colors mark the zones of active deformation. Below, we have the phase composition diagram, and to the right, we have the uplift rate evolution from map view with the blue colors showing the subsidence and brownish colors showing the uplift. What we can see here is that the rift initiation is linked to the extensional reactivation of the suture zone. The first sedimentary deposit forms above the suture zone, then the deformation migrates in space and time, generally towards the basin center. Fastening of the lithosphere is observed above the astenospheric upwelling until breakup occurs right about now. Yes, and the oceanic spreading starts. Yeah. This is the same model at certain time steps. I'd like to draw your attention to the crustal melting that is observed at the base of the crust. Here, the localized crustal thinning and the thermal heating effect of the upwelling hot asthenosphere initiates the partial melting of the crust. As the deformation migrates in the upper crust, these melts actually contribute to focusing the deformation towards the basin center via thermal and melt-induced weakening effects. This is then followed by the wide-scale decompressional melting of the uplifting asthenosphere. Then mafic melts are then extracted from the partially molten mantle domain and accumulate along the moho, leading to underplating. First continental breakup occurs at around 10 million years and then leads to oceanic crust accretion and spreading. In contrast, we have three different oblique rift models here. The first one with a very low 10 degree, the other one with a 30 degree, and the last one with a moderate 50 degree obliquity. Please note that I changed the color scale for the effective viscosity maps. So now the darker colors show the active deformation. The rift initiation is still connected to the extensional reactivation of the inherited suture zone. However, the more oblique the rift is, the less efficient the strain localization becomes. This is also evident from the complex depocenter geometry and also from the fault patterns, which also include strike, slip, transverse zones, and oblique normal faults arranged into an echelon fault patterns. Due to this strain partitioning effect, the lithosphere thins at a lower rate in more oblique scenarios. Therefore, the breakup occurs later in time, and the resulting lithospheric structure shows along strike variations in the crustal structure, crustal strictness, thermal structure, and lithospheric strength. Now let's see how all this influences the syn-rift magmatism and spreading initiation. First of all, because the lower thinning rates in more oblique rifts correspond to lower thermal gradients in the lithosphere, we can assume that oblique rifting should somehow influence the melting during rifting. In our models, we observe two types of melting: widespread decompressional melting of the upwelling mantle and highly localized partial melting of the crust. Here I plotted the overall amount of partial melt volume present in the whole model domain in case of different orthogonal or oblique rift scenarios. First, you may notice that the onset of melting is delayed with increasing obliquity. But however, while there's a significant nonlinear decrease in the produced crustal melt supply with increasing obliquity, In case of the mantle melt volume shows rather similar, just delayed growth rates in time, regardless of the obliquity of the rift. So the reason for this is that oblique rifting mostly affects the strain distribution within the crust, where the crustal structures control the exact temperature and pressure field that is essential for the melting, but the mantle remains mostly unaffected.
You're now at 11 minutes.
Yeah, thank you. Another interesting aspect of our models was that superimposed over the along strike consistent general upwelling of the mantle, the crustal melting showed the same on-echelon arrangement as the crustal structures, which suggested that there's a strong structural control over the crustal melting. At the same time, this melting provides positive feedback to the deformation by locally increasing the strain localization, and therefore it allows to further focus the deformation to these suborthogonal rift segments and stabilize on a long term this segmented structure of the oblique rift. These results seem to be in good agreement with observations from oblique rift systems worldwide. These observations often indicated that oblique rifting could control the orientation of some magmatic diking, or could confine the volcanic ridges or eruptive centers to certain magmatic segments, like something we see in the main Ethiopian rift, where these magmatic segments are colored with these yellow polygons. And the geometry of these magmatic segments here show a strong resemblance to our modeled n-echelon arranged melting zones. When the continental rift evolution approaches the continental breakup stage, the segmented rift structure will control the location and mode of spreading initiation. The first continental breakup always occurs along the least oblique rift segments, because these segments sustain the highest rift perpendicular extension, and therefore they are the most thinned, heated, and weakened parts of the lithosphere. At first, small embryonic basins, oceanic basins develop, and then they propagate in two directions laterally until the individual segments merge into single oceanic domains. The mode of this ridge linkage depends on the obliquity of the rift, with obliquity angles higher than 30 degrees, promoting the formation of such proto-transform faults over continuous linkage via curved normal faulting. And this also means that oceanic transform faults may develop spontaneously during the late stage of the oblique spreading initiation if the obliquity exceeds 30 degrees. These inferences are also in line with some observations, for instance, from the westward propagating woodlark basin, where the younger western side of the basin show small, isolated, n-echelon arranged oceanic basins embedded into highly thinned continental crustal domains, which should suggest that seafloor spreading has initiated along originally offset spreading centers, whereas in the older eastern segment we see well-developed transform faults, separating some of these offset spreading centers, which apparently developed during the later stage of the spreading initiation. Yes, so the take-home message would be that the oblique rifting seemed to have the highest impact on the structural and magmatic evolution of the crust, but not the mantle. And also, the higher the obliquity is, the more distributed the deformation is, the more delayed the onset of melting and continental breakup is, and there's more chance for the formation of spontaneous transform margins. Thank you.
Thank you, Eva. That was a wonderful, wonderful talk. There are some questions coming up in the chat. Jean-Baptiste, would you like to unmute and ask your question? Or would you like me to read it? Okay, perhaps I will read it. Your results show that the timing of breakup is a function of the obliquity of pre-existing structures. If I were to extrapolate your results, I would anticipate that breakup occurs latest where pre-existing structures are parallel to the extension direction, i.e. perpendicular to the active rift, i.e. at margins more likely to develop major transform faults. Have you modeled this for pre-existing zones of weakness oriented perpendicular to the active rift?
Completely perpendicular? No. Just the maximum obliquity that we modeled was this 50-degree obliquity, mostly because I think because of the boundary conditions, we started to see some unrealistic results about that.
Okay. There's another question from Adina Pusak. Would you like to ask your question, Adina?
Yes, I can do that. Hi, everyone. And thank you, Eva, for the presentation. I was wondering, because you showed very nicely that the obliquity actually delays the onset of breakup and magmatism. So, and the most efficient case is orthogonal rifting. So just wondering if actually the degree of obliquity we observe developed after breakup and not before.
Oh, can you repeat your question because I didn't get it?
Sure. So I was wondering if the most efficient case for breakup of a continent is orthogonal rifting. I was wondering if the degree of obliquity we observe actually developed post-breakup and not as an imposed feature of the model.
What do you mean that the obliquity we see? I mean, in our models, we define the obliquity of these rifts based on the orientation of the weak zone that we imposed. So I don't understand what you mean.
I'm wondering if that obliquity could develop due to other factors of the dynamics of rifting.
All right. I don't know, but I think in the way we interpret our models, no. Okay. Or at least how I define the obliquity here.
Sure. Thank you.
Sorry.
Okay, there's a bit of an explosion of questions occurring in the chat, which we won't be able to get to in the interest of time. Maybe just to follow on Jean-Baptiste's question from before, he just asked what kind of unrealistic results did you find? And then beyond answering that question, we'll maybe move to you answering them in the chat during the next talk. But could you answer what kind of unrealistic results?
Well, not that specific, but you know, when we tried with the 60-degree obliquity, the most of the model domain, how to say, seem to be distorted, or the structures, I don't know how to say.
You mean like warped? They got warped or something?
Yeah, it you know, I always cut some domain from the edges to avoid the boundary effects, but in this case, after this 50-degree obliquity, width of the distorted boundary effect zone increased like suddenly a lot. So there was nothing in between to really realistically interpret, if you know what I mean.
That sounds fair.
Yeah, sorry.